Good afternoon, everyone. Good afternoon. Thank you. All right, let's get started. We're looking at the second order step response, and we completed it, but I want to go through some of these details again. Okay, so thank you. So second order step response, we start off with the second order equation. You're looking purely at forced response only. So we have 0 initial conditions. Okay. Then we divide through with the mass. We obtain it in the standard form. U of t is a unit step function. F naught times U of t is a step function which is magnified by an amount F naught. Okay. Divide through by M. This is what we end up getting, okay? Where zeta and omega n have the customary meaning. Zeta is the damping ratio, omega n is the natural frequency. Omega n squared is A by m. Zeta is C by 2m omega n, okay? Then we do the Laplace transform on both sides. We go through the partial fraction decomposition. We obtain the system response as the following. X of t ended up being F naught by k, 1 which is U of t, but I'll just say it is 1 because we're looking at response for t greater than or equal to 0. So this is 1 minus e to the power minus zeta omega n t divided by square root 1 minus zeta square times cosine omega dt minus psi. Slightly varying from what the book presents, but I showed you the equivalence between this and what the book does in the previous lecture. Okay, so this is the same thing as what your book says. Nothing different. I'm just writing it as a shifted cosine wave. Your book writes it as a shifted sine wave. No difference between the two. All right. And then psi here is tan inverse theta by square root 1 minus theta square. So this is the system response that we obtained, and one can plot this as a function of time, which is what I'm showing as a generic plot here. This is time. This is the response. There are some salient features on this plot that I want to talk about, and we will solve a problem to reinforce all this. We have a peak point x suffix p. Then we have a steady state value for the system, which is x steady state, which is this dotted line that I've drawn. This point is x steady state. I'm also going to mark a point where the response first reaches half of the steady state value. So that's about here. 50% of the steady state value. The time taken to reach 50% of the steady state value is the delay time, t suffix d. And we're going to write down all these things today, okay? Then the time taken to reach the steady state value first after this plot has started, which is this point right here. This is called as the rise time or the 100% rise time. I'm reaching 100% of steady state value right at the time, the first time. Then I have the peak point, the time at which that occurs is the peak time. T suffix P is the peak time. The time taken for the system response to reach to 2% of the steady state value is a settling time. Okay, so somewhere here. X of t is approximately 2% of the steady state value. This time taken to reach there is the settling time. Ts. The maximum peak overshoot was the difference between steady state and the peak value. Right here. M suffix p. Okay, now we are going to write down all these things. Start with the steady state value. X steady state is nothing but the limit of the system response as time goes to infinity. Which, as you can see from the solution, is f naught divided by k. If I have a unit step input, the value of f naught is 1, so the steady state value is 1 by k. Okay? Then delay time, t suffix d, is the time taken to reach 50% of steady state right after the start of proceedings. From the start. One can derive an approximate expression for the delay time in terms of the system parameters. I'm going to write that expression right here. So Td is approximately 1 plus 0.7 zeta by omega. Okay? So this is an approximate equation, one can derive it. We're not going to derive these things. Then I have the third one, which is called the rise time, okay, Tr. I'm going to write it here. Tr is the 100% rise time. Time taken to first reach the steady state after the start of the problem, as you can see. Okay, so time to reach 100% of steady state value. After start. We have an expression for T rise. I have derived it in my lecture notes. I will not be deriving it here. Okay, here is the expression. So T rise is pi by 2 plus psi divided by omega d, where omega d is omega n times square root of 1 minus zeta squared. If you look at your book, the expression will be slightly different. Okay, so if you look at the book, T rise is 2 pi minus phi by same denominator omega d. They're all the same because phi and psi are related. So phi, which is tan inverse this is the definition from the book, okay, and the relationship between phi and psi once again, these are explicitly shown in the lecture notes that I have posted last class. Yes. That is supposedly zeta, yes. Okay. And then I have a couple more things to write down here. The peak overshoot, so MP is xp minus x steady state, and xp is the peak value. The percentage peak overshoot can be written now as the following. Percentage MP is 100 times expressed as a percentage of the steady state value. Once again, the derivation is there in my lecture notes. We did that derivation last time in class. Okay, and here is the expression for the percentage peak overshoot in terms of the system parameters. So we have percentage MP is 100 exponent minus pi zeta one minus zeta square. Okay, this zeta is the same as that zeta. I just wrote this a little quickly. And Tp is the peak time. We derived this as well in the last class. Tp is just pi by omega d. I put a box around this as well. And the last one is settling time. So Ts settling time. It has the same idea as what we do for a first order system. A first order system, when does it settle down to steady state? Is when it crosses past 4 times the time constant time. Exactly the same notion here as well. So Ts is time taken to reach within 2% of steady state value. Even if you forget everything about this course, don't forget settling time. It's 4 times tau. Okay? And what's tau for a second order system? By zeta omega. Okay. Typically, for underdamped systems, one does not use the settling time, but it is still a valid approximation. It is still a valid expression for whatever type of damping you use in a system. Okay. This is still valid. If you have an overdamped system, the notion of a damped frequency makes no sense. Okay? If you have an underdamped system, you have a damped natural frequency, which is omega d, and then you also have the settling time. So typically for overdamped systems, the settling time is the main thing. That is the thing that tells us something about the system. For an underdamped system, it is the damped natural frequency that tells you something about the system. Okay? Alright, so with all this said, I'm going to pull the top panel down. We're going to solve one more problem, okay, using these ideas, and then we're going to move on to what is called as the transfer function of a system. Okay? We're going to go into alien territory. Probably this is alien territory for many of us, but it's going to be even more so alien as I'm going to go further down the line. Okay? We're going to go into frequency response analysis. Whatever we are doing now is called as time domain analysis, because the system response is presented as a function of time. X is a function of time. In frequency response, we present the system response as a function of the frequency of operation of the system, of the forcing function. Question?
Would it make sense to have a time constant for an unstable system?
Oh, absolutely. You just take the magnitude of it. So what is the time constant for an unstable system? Is the time taken to just blow up, essentially, right? I mean, it does not have any physical significance, but you could still give a magnitude to it. So it makes no sense in some sense, but it also does make sense in some sense. Yes?
So the time constant for all second order systems is always t. It's always 1 over omega n.
Yes, that's what I'm saying. Yes. Okay. example. So you're told that a second order free response shows oscillatory behavior, or a system shows oscillatory behavior. A free response of some system shows oscillatory behavior. Which immediately should ring a bell in your head. What is the best way to model oscillatory behavior is by modeling the system as a second order system. Right? Because first order systems, the free response cannot exhibit oscillatory behavior. Okay? So then they say further that for a unit step input, the steady state value of the system is 4 centimeters, x of t. You're told that the percentage peak overshoot is 20%. And you're told that when time is 0.5 seconds, the system response has a magnitude of 2 centimeters. Okay, so at after start. Obtain the system ODE. Obtain the system model, okay, mathematical model. Before I erase everything, question, after you take this down. What do you think this statement is telling us? The statement that at half a second, I am at x of t of 2 centimeters, what does that statement tell me? Yes?
The rise time?
Rise time. Yes?
That's the 50% value?
So 50% value, so it's the delay time. Okay, so it's telling you that the delay time is actually 0.5 seconds. We have an expression for the delay time, right? So we can make use of it. So read the question very carefully, please. And after all of this has been ingrained in us, these should be second nature. And I will make sure it is ingrained in you. So I have the following. X steady state is 4 centimeters. By definition, this is F naught divided by K. Is 4 times 10 to the power minus 2 meters. What is F naught for our problem? It's a unit step input to the system, so F naught is equal to 1. Okay? So look at this system. It is a unit step input. Please read the question. Sometimes it may appear as if the details of the problem are not given to you. They will be given to you. They will be embedded within the wording of the problem. Okay? So we are given unit step input, which means that F naught is 1 Newton, right? Let's assume Newtons. And so I can find out K. So 1 by K. So that K is 25 Newtons per meter. Right? 100 by 4, 25 Newtons per meter. So you're done with the first of these culprits. And then we write down whatever we know about the system after this. Okay, so we know that at x of t is 50% of x steady state, which means that the delay time is 0.5 seconds. And we had an expression for t delay, the approximate expression, one can use it. So this is equal to 1 plus 0.7 zeta by omega n. This is completely useless because neither do I know zeta nor omega n. Then you backtrack and say, okay, what else is given to me in this problem? I'm given the peak overshoot percentage, so perhaps that could give me something. Okay. Does this make sense to everybody so far? Yes.
Where are you getting the one, that term, that's the time rate term?
Say that again, please.
Where are you getting the time rate term? Like, I know it's 0.5, where are you getting the other side of the one?
This is the expression that we just wrote down, which I just erased here
Okay.
at the beginning of the lecture. Right. That's an approximate expression. We are not going to derive it. But you can derive it. You just substitute the system response to be half of the steady state value. Equate it on both sides. This is approximately what you get. Okay. All right. So here is what we have. Percentage overshoot is given to us. Percentage MP, which is 20. We have an expression for this, which we derived last class. Don't forget the factor of 100 multiplied by exponent I have this, then this, two equations, two unknowns. One can solve for zeta from the percentage overshoot and then substitute and get omega n from here. I'm going to skip all those steps. Yes, question.
Kind of a question about the percent overshoot equation. The reason it's exponent of pi times zeta is because the percent overshoot is looking at the time after pi, like half a cycle. Is that like that pi?
No, the pi doesn't come from there. The pi comes from the fact that the peak time is pi divided by omega d. Okay, so that's where the pi comes from. That is essentially, if you're, maybe I should. We did this last class, but very quickly. Xp is x at t is equal to t peak. So if I substitute for t is equal to t peak in the system equation, in the system solution, this t peak is pi by omega d. That's where it comes. Okay. All right, I'm going to continue with this problem. So from the percentage overshoot, I can solve for zeta. So use percentage MP equation. We'll obtain zeta to be around 0.46 or something. 0.46. Once you obtain zeta, substitute it into the delay equation. Okay. Then I have 0.5. 1 plus 0.7 times divided by omega n. Basic substitutions. There is nothing funny or tricky here. Omega n is 2.6 something, 2.64 radians per second. How do I calculate mass? How do I calculate the mass of the system? Yes.
Omega n equals square root of k divided by m.
Omega n is square root of k by m, or omega n square is k by m. So the mass is k by omega n square, which gives me 3.6 kilograms. Once I have the mass, once I have the natural frequency, once I have the damping ratio, I can calculate the damping constant, okay, which is C by m. And here's what I'm going to do. I know these are a lot of things to remember. No sane person other than the person who teaches this class will remember it. So, I'm going to have a list of all of these written down on a piece of paper, post it on card. Okay? But please remember how you got these things. That's more important. So C by m is 2 zeta omega n, so C is 2m zeta omega n, which I get to be 8.7 Newton seconds per meter. Okay, system model is easy to write now. Mx double dot Cx dot Ax subjected to a step input. Okay, F naught is 1, M is 3 point something, C is something, and K is something. So this is 3.6 x double dot 8.7 x dot. K is 25, 1 times u of t. This is one way of writing the system model. The other way is by just dividing through by the mass and writing it as in terms of zetas and omega n's. So the other way, x double dot zeta omega n x dot omega n square x is f naught by m. U of t divided through by the mass. Substitute. So this is x double dot. Product of all of these gives me approximately 2.6 or something x dot, and then 2.64x is 1 by 3.6. So both of them are okay. You can either write the system model this way or you can write the system model this way. This is preferable because when you're taking the Laplace transforms, you always want to make sure the highest derivative has a coefficient of 1. Okay? Yes, question?
That's what I was just going to ask about. Which one you prefer.
It's not about what I prefer. It's about what is pertinent to the solution that you want. Okay? I would prefer to be outside. All right. Any other questions, please? Yes, yes, yes.
If you divide the first equation over by mass, it'll get the same thing.
Absolutely, absolutely, absolutely. That's what I did. That's why you have this 1 by m here. Absolutely. Some other hand was raised on this side. Any questions, please? Okay. We're going to move on to uncharted waters. And this is called the transfer function analysis of systems. Okay, or transfer functions of systems. Some of you who have had recitation today and who chose to go to recitation, you would have had a taste of this. Okay? You're going to see why we are doing it to a certain extent. And as I said at the beginning of the class, all our system responses so far have been in the time domain. Right? We get x of t is equal to something, it has a time component to it. That's great, that's fantastic. I like the time domain analysis because I can visualize the system behavior. Okay, I see something oscillating, I know that the system is going to bounce and jump and go forth. But for certain problems, predominantly if you look at electrical signals, electrical input functions, these are in the form of voltages or currents, alternating currents. Alternating, currents have a sinusoidal component to them. And all these inputs in the electrical domain have a sinusoidal component to them. So functions that are sinusoidal are called as harmonic functions. They make you dance in harmony with themselves. That is, if I have a harmonic input to a system, the output is also going to be sinusoidal or harmonic. That's why there is a harmony between the input and the output. That's why they're called harmonic signals. Okay? To study harmonic signals or functions or harmonic inputs, it is best to visualize them in the frequency domain. What is the magnitude of the wave that I get? What is the time period of the wave that I get? The time period is obviously related to the frequency of the wave. And so we are going to slowly position ourselves to study frequency response of systems. This is an important component because you're going to take a course, at least from a narrow perspective, you're going to take a course called measurement systems. In measurement systems, all measurements typically are done in the Fourier domain. And in the Fourier domain, frequency analysis is what you'll be doing. Okay? Alright, so with that very brief introduction, let's go to transfer functions, which will help us analyze systems in the frequency domain. Okay, we don't know how, but I'm going to go there slowly within the next week. Okay, transfer functions. The name implies what it means. It is a function that transfers something. That's all it is. Okay? And here is the definition. Two things, two caveats. One is it's always defined in the Laplace domain. Okay? The S is equal to sigma plus j omega of the Laplace domain. And when you're doing transfer function analysis, you switch off the initial conditions. So initial conditions are no longer on for us. When we perform transfer function analysis. Transfer function analysis or frequency analysis typically is a name given to it. We'll start off with this and we'll start applying the frequency term when we see the frequency term. We haven't seen it yet. S is the Laplace variable. I hope you all recognize this creature. Just a complex number. Of course, there's a whole story on why we operate in the complex domain. I will not go into it today, but we will be doing electrical systems very soon. You are also taking a class on circuits. Some of you may have already taken it. We will see why we are doing this analysis in the complex domain. Okay? All right, so transfer functions, here's the definition. Is T of S. So as you see, this is in the Laplace domain, defined in the Laplace domain. This is the Laplace transform of the output function divided by the Laplace transform of the input function. What's the output function? Output function is the dependent variable that we have been working with in all our ODEs. Okay, so if I have an equation of motion x double dot is equal to f of t, then the output variable is x of t, the input function is f of t. Okay, so for example, if I have x double dot is equal to f of t, the output function, or the dependent variable, is x of t, the input, f of t. Okay. Let's take an example, write out the transfer function, then we will see why it is useful. I'm not going to go into the whole story of transfer functions because you're going to see these again and again. And you'll be seeing this again in control systems, which is the next sequence of this course. So things should become more clear then. Okay. So let's take an example. x double dot dx dot 2x is equal to some g of t. Obtain the system transfer function. From now on, my shortcut notation for this is TF. Okay. How you do this is by taking Laplace transform on both sides and switching off initial conditions. So switch off initial conditions. Then take Laplace transform on both sides. If I switch off initial conditions, x double dot, the Laplace transform of that is s square times x of s. So I have s square x of s. Then the Laplace transform of x dot is just s times x of s. So 3s x of s. Laplace transform of 2x is 2 times x of s. Laplace transform of g of t is capital G of s. Something. The Laplace of and the Laplace of x of t is x of s. Okay. Take the x of s as a common factor, take it out, and so I have s square plus 3s plus 2 is equal to g of s. And so the system transfer function t of s, which is Laplace of the output function or the dependent variable or whatever is our variable of interest that we are solving for, which is x of t. So the Laplace of that is x of s divided with the Laplace of the input function, which is nothing but 1. If I just take the ratio, s square plus 3s plus 2. This is the transfer function. People in the back, can you see my writing? Somewhat or okay? Please let me know if I need to write larger. Okay. I want to stop and see if there are any questions so far. Transfer function is Laplace transform of the output function, which is a dependent variable, divided by the Laplace transform of the input function, which is the input to the system. Okay. Question.
So can the transfer function be thought of as the inverse force function?
Inverse of what?
Force function?
Not really, right? Because you also have the output variable sitting on top. Yes, question.
Why do we turn off the initial conditions when we do this?
That is because the transfer function analysis is typically performed for a steady state behavior of the system. Okay? So the initial conditions don't play a role in a steady state. For a stable system, the initial conditions contribute only to free transient response. Transient response decays after some time. Okay, the question asked was, okay, why are we switching off initial conditions? Excellent question. The reason is because this transfer function is going to be applied to study the steady state response of systems. When you study the steady state response, the initial conditions do not play a role for a stable system because initial conditions contribute only to transients. Their effect decays off after time. Okay, for a stable system, as you know. Alright? Okay. Why are we doing these things? 3 reasons, very short reasons. The 4th reason is a whole course, which is control systems. The first reason, primarily for us, very narrow-minded people that we are, is transfer function is useful for frequency response analysis. Okay? The transfer function is useful for analysis of systems in the frequency domain. here is a question. I have the transfer function there. This is the example that we started off. Look at the denominator. What do you call the denominator polynomial? What do you call it as?
Characteristic polynomial.
The characteristic polynomial. What's the advantage of knowing the characteristic polynomial? Fantastic. I know the roots of the system, so that will tell me if the system is stable or unstable. Beautiful. So if I know the transfer function, I know the system stability. That is another great utility of the transfer function. Okay, so tells us about the system stability because the denominator of the transfer function contains the characteristic equation or the characteristic polynomial. In my notes, I have listed a few more reasons. I'll just state the third reason, I won't go into it. The nice thing about transfer functions is you can perform experiments, carefully curated experiments, to known inputs and obtain the system transfer function by understanding the behavior of the system. This is exactly what we've been doing so far. I give a step input to the system. I have a known input to the function, to the system. I can extract some of the coefficients of the system. If I know the coefficients of the system, I know the transfer function of the system. If I know the transfer function, I know the stability of the system. If I know the transfer function, I can then jump on to frequency domain analysis. So that's the beauty of transfer function. Okay? Two more things I want to do before we close off shop today is the first thing is an example, another example. Let's say I have the following system. Okay. So 3x double dot plus 2x dot is equal to f1 of t 2 times f2 of t. So there are two input functions to the system. Okay, f1 of t is an input, f2 of t is another input, and we have studied systems of this sort, right, where you have a complicated forcing function, you break it up into smaller pieces. What's the system transfer function? So depending on the number of inputs to the system, you will have as many transfer functions for the system. Okay? So we have to define, because the system has two inputs, we have to define two transfer functions for the system. The first transfer function is going to be for just the effect of f1 of t. The second transfer function is going to be for the effect of 2 times f2 of t. Okay, so you break the system down, superposition. And then 3x double dot, 2x dot is 2 times f2 of t. Take Laplace transform on both sides. So this is 3s square plus 2s x of s is equal to f1 of s. No initial conditions. When you talk about transfer functions, no initial conditions. Okay, we've gotten rid of that. 3s square plus 2s is 2 f2 of s. Take Laplace transform on both sides. The first transfer function of the system is t1 x of s by f1 of s. That's 1 by 3s square plus 2s. Second transfer function is with respect to x of s and f2 of s. What's the effect of the second input? So p2 of s is Laplace of the output. There's only one output to the system. We are not studying multiple outputs. Multiple inputs are fine. So this is going to be 2 by 2s. These are the system transfer functions. So 2 transfer functions for the system. Any questions, please? Yes, yes.
I just had a question for something number 2, you started with something. Why is that any different than just doing a regular Laplace?
A regular Laplace transformation?
Yeah. Like, because you can find the roots and determine the stability of the system.
Of course you can. I mean, what I'm saying is, suppose I perform an experiment and somebody gives me the transfer function and says evaluate the stability. Then I know that the transfer function contains the characteristic polynomial.
So there would be like no difference between like you have to choose between primary transfers.
Can you say that again, please?
So like there'd be like no difference if like you're just given a function between trying to find the transfer function and or they're doing a Laplace transformation just to determine the stability.
Right, absolutely. So from the point of view of stability, you could do it two ways. One is if I know the transfer function, I know the characteristic polynomial, I find the roots of it and figure out the stability. If I'm not given the transfer function, but if I'm given the ODE, I can still find the characteristic polynomial. So both ways are fine. Yes, yes, two hands, one first time and second.
Why can't you like define a new function f3 as f1 plus 2f2?
You could.
And then just have a single trigger?
You could. But the utility is lost, right? Because I'm using the principle of superposition and I'm trying to simplify the problem. And sometimes what I would like to do is, okay, there are two current sources for my circuit. I want to understand what the first current source is doing, what the second is doing, and then add the solutions together. You see, that's the utility of this. But you are perfectly fine. I mean, I can call this as a G of t. Absolutely. You had a question too.
Yeah, is there any way of looking at the transfer function that makes it easier to analyze in terms of stability, or is it just like you still have to go in and then like find the roots based off of it?
You still have to, yeah. I mean, some work has to be done still, of course. But at least if I know the transfer function, I have an idea about the stability of the system, which is where I'm headed to next. Okay. I'm now going to take an nth order ODE. This is a scary beast. So, nth order ODE meaning this is of order n. Right? This is d to the power n x dt to the power n. This is the coefficient, the n minus 1th coefficient. dn minus 1x dt n minus 1. Go all the way. I get the second, first, and the 0th coefficient. So a2 b square x by dt square. a1 dx by dt. a0 x. This is the system ODE. And let me say that the system is subjected to an input which is of the mth order. Okay? So on the right hand side I have a differential equation which is of the mth order. So that's Bm d to the power m f dt to the power m minus 1 plus B2 so here the dependent variable is x of t, the input function is f of t and its derivatives, all of them. Okay. So here the dependent variable x of t. With your permission, I'm going to erase this particular panel here. Okay. What's the system transfer function?